So next we're going to practice predicting the molecular geometry for the diagrams that we drew earlier. We already did NH3 as the example on the previous slide. It had 4 electron domains, but one of the domains was a lone pair. So if we erase that portion of the tetrahedral shape, what we have left is trigonal pyramidal. Trigonal pyramidal is tetrahedral with one part removed. The next one we're going to try is carbon dioxide, since that's one that we drew together. The first step is to count how many electron domains there are around the central atom. Carbon is the central atom, and I see that there's a double bond here and a double bond here. So that's just 2 domains. In this case, the electrons are all clustered on either side of the carbon because it's forming double bonds with the oxygen atoms, so there's only 2 domains. If you remember, when there's only 2 domains, the molecular geometry is going to be linear. And so we can just fill in linear for carbon dioxide. And let's center this so it's more pleasing. The next one that we drew together, I believe, was CH4. So let's take a look at CH4. CH4 has 1, 2, 3, 4 electron domains. So we could go ahead and fill that in the chart, and that would give it a tetrahedral geometry as its base. See if this will let me change the slide. There we go. So 4 electron domains would be tetrahedral. And in this case with CH4, it's a little different than NH3 because it doesn't have a lone pair at the top. And so there's nothing to erase. So CH4 is going to keep its tetrahedral geometry. So we'll go ahead and fill that in. Here we go. So CH4 has 4 electron domains, and since they're all bonded pairs, they all have atoms on the ends, we would have tetrahedral for the shape. Another way that you could determine these is by building them. So if you go ahead and build some of these molecules using the molecular model kits, they should form the shapes that you see here, especially if your models use the right colors and the right number of bonds. The next one that we did together was SO2. So let's skip down to SO2. If we look at SO2, it has 1, 2, 3 electron domains, right? Because of that one double bond, it has 1, 2, 3 electron domains. We could go ahead and fill that in. And then if we remember that 3 electron domains gives us a trigonal planar shape, right? So the base is going to be a trigonal planar shape. That's the one that looks like a triangle and it's flat. So SO2 is going to start out with that shape where there's 1, 2, 3 regions. But then this lone pair is going to be eliminated. So we start out with a triangle shape, but we eliminate the top portion. And what we have left is a bent molecule. So if you take a trigonal planar molecule and you eliminate the lone pair, what you have left is a bent molecule. And if you try building that one with the model kit, you'll find that that is true. And then the last one that we did together is the one that was a little bit more complicated because it had carbon, oxygen, and hydrogen. It was formaldehyde. If we count the electron domains, we have 1, 2, 3 electron domains around carbon. And none of these are lone pairs, right? They're all bonded pairs. So this one is going to start with trigonal planar, just like the last one, triangular shape. But it's going to keep that shape, trigonal planar, because they're all bonded pairs. So let's see if I can get this to, there we go. So that's this one here on the bottom. It had 3 electron domains, and its molecular geometry was trigonal planar. Next, you could try labeling this ethanol molecule with its geometry once you complete the chart. And in this case, there are a few central atoms, right? So you would want to look at each central atom and label it as either tetrahedral, trigonal pyramidal, trigonal planar, bent, or linear. So with more complicated molecules, we talk about the geometry around each of the central atoms. So you could go ahead and try that.